In this video, we're going to introduce the idea of probability by talking about some terminology we're going to use and just make sure we're comfortable with that before we actually try to compute some probabilities. Although here I will make use of your intuition and try to do some simple ones that hopefully you'll believe me of what the probability is. So first of all, probability is the mathematics of chance. So it's the numerical measure of the likelihood. So we're always talking about likelihood that something will happen. Okay, we usually call these things events. So first of all, an experiment is an activity with an observable result. Okay, so something happens from the experiment. Each possible result is what we call an outcome of the experiment. Okay, so I'm going to give some examples. Okay, so experiment, and then their outcomes will be underneath, possible outcomes. So the easiest one that gets used a lot in probability is flip a coin. Okay, so this is an experiment. When you flip a coin, you either get heads or tails. So your outcomes are going to be heads or tails. Okay, you could also roll a die. Okay, then your outcomes would be the numbers 1, 2, 3, 4, 5, 6, assuming that you're rolling a 6-sided die, which is what we normally have. You could also survey a group of people. Okay, this is another type of experiment. Okay, so each person's answer will be an outcome. Okay, so these are their answers here. Okay, so it depends on the type of survey, what the outcomes will look like. If they're multiple choice, then you can have like A, B, C, D here. If they're giving word answers, then you're going to get a whole bunch of outcomes depending on what they say. Okay, but those are some examples of what an experiment might look like and what its associated outcomes might be. Now, if we put all of these outcomes for a particular experiment in a set, we call that set the sample space of the experiment. So if you have all the outcomes, everything that could happen in your experiment is in one set, that's the sample space. We usually denote that with a capital S. Okay, so when we're talking about the sample space, we're going to use a capital S. Now, an event of the sample space is just a subset of the sample space. So E is an event if, remember this notation, this says E is a subset of the sample space S. Now remember what it means to be a subset is that E just contains some of the elements of S. Okay, any number of them. So E contains things that could happen when you perform the experiment. So then we say that event E has occurred when we perform the outcome. If the resulting thing is actually something from E, that's when E is going to occur. Okay, so let's just think of a basic example. So suppose our event is to roll a single die, and let's just say here it's a 6-sided. Okay, so what would our sample space look like? So it's S, it's going to be a set with all the possible outcomes. So when we roll a die, we already said the possible outcomes were the numbers 1 to 6. So if we put all those together, they form our sample space. Okay, now we want to define an event for the sample space. Okay, you can do this in a variety of ways. Okay, so I'm going to do a couple here to show you. So I'm going to call it E1 for event 1. Maybe it's the event that you roll an even number. Okay, so then E would contain the outcomes 2, 4, and 6. Okay, you could have E2 be the event you roll a 6. Okay, then E2, just has the outcome 6. Or maybe you just want to define an event by its outcomes. Okay, so E3 is the event that 1, 3, 5, or 6 is rolled. Okay, you can do these any ways you want. And then we would say, we would do the roll. Okay, so we'd roll the die. And if we got a 6, then we would say E1, E2, and E3 all occurred. If we rolled a 2, then we would say E1 occurred, but E2 and E3 did not occur. Okay, so that's the idea. There's a couple of special events. Okay, so if the event has no outcomes, we call it impossible, because when we do the experiment, it's definitely not going to happen. So if E is impossible, then E, the event, is just the empty set. Okay, remember that the empty set is a subset for all sets S. Okay, so the event, the empty set, is also an event because it's a subset. If we have all of the outcomes, then we call it certain, because when we do the experiment, it definitely has to happen. So if E is certain, then E actually is all of S. Okay, so it contains, every possible outcome. Which means that it will definitely occur when we perform the experiment. Okay, so those are just some special events. Now, let's say we consider the experiment where we roll 2 different colored die, six-sided die, okay, and we record the top face of each. So here, the sample space is a little bit harder to find. Okay, so I'm going to make it really big. So outcomes are going to look like, I'm going to do them as ordered pair. Okay, so let's call it, I'm going to call it X and Y. Okay, so X is the number on die 1, and Y is the number on die 2. Okay, these are different colors, so we can tell which die the number occurred on. Okay, so that's what our outcomes are going to look like. So when we write them, okay, I could have the outcome 1, 1. I could have the outcome 1, 2. I could have 1, 3. Okay, and so 1, the outcome 1 could occur on the first die, with every number from 1 to 6. Now maybe the first roll, the die 1 was not 1. Okay, maybe it was 2. Then it could occur with 1. It could occur with 2, 3, etc. up until 6. Okay, and we can do this all along, down as well. So the first die could be 1 through 6. So I get this sort of grid-like sample space the way I've written it. Now with our counting techniques, we should be able to tell that the number of things in this sample space should be the options for die 1, which are 6, times the options for die 2, which is 6. So there should be 36 elements in this sample space. Okay, so that's one way you could write it. Now notice that I have these outcomes 2, 1 and 1, 2. Okay, and there's lots of pairs like that. So 6, 1 and 1, 6. Okay, so the order matters because the die are colored. Okay, so we can tell where they occur. Okay, so that's what our sample space would look like. Let's think about some events for this. So let's let E be the event that the sum on the 2 dice is 8, and F is the event that at least one of the die is a 3. Now, because the events are just sets, okay, in particular they're subsets of S, all the stuff we studied in chapter 1, so the intersection, the union, and also complements, they all still apply. Okay, so in order to complement, okay, so our S is like our universe in chapter 1. Okay, so because it's everything that could occur. Okay, so that's the universal set. So we call it sample space when we're talking about probabilities. So if those are our 2 events, we can write what is in E intersect F and E union F. Okay, I'm going to start by writing what is in E though. Okay, so E is the event that the sum on the two dice is 8. So I want all the ways I could sum to 8. So they have to be in F, so they're ordered pairs. Now, if I have a 1 occurring, I need it to match with a 7 in order to sum to 8. 7's too large to appear on the dice, so I don't have that. But I could have a 2 and a 6, okay? Which also means I could have a 6 and a 2. Okay, so remember, those are different outcomes of our experiment. Okay, now I could have a 3 and a 5, or I could have a 5 and a 3. And then lastly, I could have 4 and 4. Now I don't need to rewrite this one, the other order, because it's exactly the same, right? If I have a red 4 and a blue 4, if I switch it, I have a blue 4 and a red 4. It's the exact same roll. Okay, so that's what's in E. Okay, F has more things, but it has all the things that have at least one 3. Okay, so now let's think about the intersection. So when I'm doing the intersection, I want all the outcomes that are in E and in F. Okay, so E doesn't have that many outcomes. Okay, so what I want to do is look for outcomes in E that would also be in F. So what I want to do is look for outcomes here that have a 3 in them. Okay, so the intersection here is just going to be the rolls 3 and 5 and 5 and 3. Okay, now when I'm doing the union, remember this one's going to be a bit bigger. Remember that I write out everything that's in one of them. Okay, so I'm going to write out everything that's in E. Okay, so those are the ones that are in E. Okay, and then I want to write all the ones that are extra in F. Okay, so that's going to be everything else. So I want to write everything that has at least one 3 in it. So I could have 1 and 3, or 3 and 1. I could have 2 and 3, or 3 and 2. I could have 3 and 3, which only occurs in that way. I could have 3 and 4, or 4 and 3. Now I don't want to do 5 and 3 because I already have that one. So then I could have 3 and 6, or 6 and 3. And that's going to be all of them. Okay, now E intersect F complement. So I still have to be in E. Okay, so I'm restricted to only these pairs. And now I want them to not be in F. So that means, so if they're not in F, it means they do not have at least one 3, which means they have no 3s. Okay, so if you're in F if you have a 3. So if you're not in F, then you don't have a 3. So then we're going to take these two, so the 2s with the 6s, and then the 4 and the 4. Okay, and that's going to be all that's in E intersect F complement. 6 and 2, 2 and 6, and 4 and 4. Okay, so I'm only doing one example like this because we did a bunch in chapter 1. They work the exact same in chapter 2. So when you're talking about events, it's just like when we were talking about sets. Now, a new word that they use in probability, but is similar to it's the exact same actually as a word we used before. So we say events E and F are mutually exclusive if they have no outcomes in common. Okay, so another way to say that is that their intersection is empty, or, okay, as sets, they are disjoint. Okay, so that's the word we used before. Okay, so it means the same thing as mutually exclusive, but when we're in probability world, we use mutually exclusive instead of disjoint. Okay, one more example. So consider event H. So we're still going from our previous one. So it contains all rolls in which at least one of the dice is a 1. So I didn't actually say what we wanted to do here, but the point I want to make is that E and H are mutually exclusive events since you cannot roll a 1 and also sum to 8. Okay, so those things can't happen at the same time, which means that the intersection of E and H is empty. Okay, now F and H are not mutually exclusive since we could compute their intersection. So it's going to be you get at least 1 3 in order to be an F, and you get at least 1 1 in order to be an H. So it's going to be 1 and 3 and 3 and 1. Okay, so there's 2 elements in there, so in particular it's not the empty set. So they're not mutually exclusive. So those are just some introduction to the terminology that we're going to use for the probability chapter.